Okay, so now it's time to actually start the stream. So basically, I'm just going to continue from the stream yesterday, where yesterday we were talking about vision transformers, so an image is 16 by 16 words. Today I'm going to go more on the paper and images with 32 tokens by the ByteDance people and Technical University of Munich. And so I'll just go into this and talk about how they were able to take a image and condense it down into just 32 tokens, so then you can feed it into other models, and it's a lot effectively easier for it to do that type of stuff. So, as usual, these guys, they have a GitHub site that has all of this, and the code's not yet out, but we can wait. But we're just gonna go through the paper and kind of understand what is it doing, how does it work, that type of stuff. So, again, the draw is here. So when diagramming ideas and whatnot, we can go here. So last stream stuff is here. I've made a new empty page, and we're gonna go from there. So, let's start. So the paper is an images with 32 tokens for reconstruction and generation, and is by a group of people from ByteDance and Technical University of Munich. And so they have a figure one right at the start. So they're talking about 32 tokens, and this is just kind of a general summary. So it's going along with the abstract. So let's read the abstract first, and then let's read through. Then let's look at the images and kind of understand what's going on. So recent advancements in generative models have highlighted the crucial role of image tokenization in efficient synthesis of high-resolution images. Tokenization, which transforms images into latent representations, reduces computational demands compared to directly processing pixels, and enhances the effectiveness and efficiency of the generation process. So they're basically just talking about here, like Gen AI, so LLMs and diffusion models. They effectively they need to tokenize images, and so tokenization effectively takes the image and it turns it into a format that's just latent space. Numbers don't necessarily mean anything except to the computer. So if we go to the draw.io, first I want to actually describe what is tokenization. I'm going to make this big because this is very important. So tokenization is, let's say you have an image, and you have some people in the image. You have an image. So what you have to do here is you just have to take the image and you just have to convert it into a format that is easy for computers to understand, which is in essence just a list of numbers, right? So it's just the process of turning a picture into a list of numbers that can be treated as tokens. So 4, 20, sure. 52, 1, and maybe we have another 4 token. Right, it's just taking the image and just converting it into a list of numbers. That's what tokenization is. That's what the paper is trying to do. So if we go back here, so that's basically what they're saying. And so this makes it more efficient, because now, we, the human, don't actually know what these numbers actually mean. Right? This is just some small part of the image, whatever. But what we are able to do is use this to train other machine learning models. Right? So now that you have image tokens effectively, what you're able to do is you're theoretically able to mix this with, say, text tokens. Right? So again, this is going to be other numbers. Let's say this is 3 digits. Right? You can mix this in with text tokens that ask about. I'll change the numbers. Right, and then you're able to have text tokens for example, what is in this image, right? So, and then you use regular NLP text tokenization techniques, right? And so you basically take this gets converted here, and so tokenization is the process of taking the actual data and then converting it into a format that is effectively easy for, say, a transformer to use, right? So now you have a list of tokens, and so I'll draw a box around this, no fill, dash lines. Right, so that's the tokenization box. And effectively, you can just take this and you can be like, hey, these tokens will just go into your LLM, and then you have your next token prediction and whatnot. And so now, you obviously want to do this more efficiently, right? Because the more you can shrink the tokens, in essence, the more information each token will contain, right? And so then the LLM, or I guess in this case, I'll just say transformer, the transformer will be able to do more higher level stuff because all of the lower level information it would have to otherwise recalculate is already part of the tokens, right? So transformers really like operating on like distinct ideas, right? And so with text, it's kind of like operating on words, right? That's kind of a distinct idea. Whereas with images, it's a little bit more complex. And that's what this paper is trying to solve. They're basically just trying to optimize the image to token process. That's the chameleon model. That we'll get to probably next stream, right? That's probably next stream. We'll get to the chameleon model that builds on all this tech. And so they're talking about prior methods such as VQGAN, typically use 2D latent grids with fixed downsampling tokens. So what they're basically saying here is, so let's just copy this. Oh. Basically, well, let's have a little bit here for VQGAN. Let's make this a little bit bigger. Right, so what VQGAN did is they basically just took the tokens and they basically just put it as like a 2D grid. Right, and then the numbers are going to be different, like obviously, but because an image is natively a 2D grid, right? So you have an image, it's natively like a 2D grid of pixels. So it feels really natural to just have it be like, oh, it's a 2D grid of tokens, right? And so then you'd feed this into the transformer, and the positional embeddings would be like, hey, this is a 2D grid. What this paper is saying, basically, and so let's continue. The 2D tokenizers face challenges in managing the inherent redundancies present in images, where adjacent regions frequently display similarities. So, in essence, let's assume you have, say, this region and this region in image, right? So you have, like, let's say, a picture of a person. And so you have, let's just say you have one set of pixels, and that contains information, like one token, that contains information on, like, skin color of the person and whatnot. But the token right next to it doesn't necessarily need to contain the same, like, let's say, skin color data or whatnot. Because the token next to it has that data. And so you're effectively duplicating the data in two different places. Right? So if you have like two people with like different skin colors, you probably need different types of stuff. But if the tokens are able to talk within themselves, then maybe only one of the tokens has the skin color information. The others don't. Right? And so there's some inherent redundancy in storing these images as 2D like representations of tokens. And so to overcome the issue, this group introduced TyTalk. So a transformer-based one-dimensional tokenizer. TyTalk. So it's an approach that tokenizes images into 1D latent sequences. So what this group basically did is just like, oh, what if we just store this in a 1D format and effectively strip out the new stuff? So I'll just... Right, so they're basically just like, we're going to store this as 1D, and we can store less tokens, and there's just going to reduce redundancy, right? So they're basically saying we're going to have a 1D list, and maybe longer one dimension, but because you only have one dimension, you're going to have a net total of having less tokens being fed to the model. Let's keep going. And so TyTalk is more compact, and so it's more efficient. So a 256 by 256 by 3 image can be reduced to just 32 discrete tokens. Right, so they're basically just saying, if you have a 256 by 256 image, and 3 color channels, obviously, you can condense it into 32 tokens. So, in essence, if you are feeding this to, say, a LLM, like a multimodal LLM, you can effectively say the image is 32 tokens. So GPT-4o, for context, has any image you feed it be 140 tokens. Right? This model, an image is just 32 tokens. Right? But this isn't an actual end-to-end model. This is just the image tokenizer part. They're able to condense the images to just 32 tokens. And as they say, it's a significant reduction from the 256 or 1024 by prior methods. And those are prior open methods. GPT-4o is going to be a little bit better because it's closed and they're not going to actually reveal it. And they're also saying that even though it's compact, it's just as good as the old state of the art, right? So we saw this with the vision tokenizers stream from yesterday. This is like they're basically saying we're matching the state of the art, but we're making it much easier to do, right? And so then later you can just take this architecture and scale it up even more. And so specifically using the same generative framework, TyTalk, which is the tokenizer they made, achieves 1.97 GFIT, which is a benchmark for how good image tokenizers are, outperforming mass GIT baseline significantly by 4.21 at the ImageNet 256 by 256 benchmark. So this is the This is the classification benchmark. So you have like a bunch of 256 by 256 images, and you have to try to classify it, right? So you have to take these images and be like, hey, that's a cat, that's a dog, and so because you're trying to classify it, you're going to be, and so it performs roughly 4% better. So the advantages become even more significant at a higher resolution. At 512 by 512, it outperforms the state-of-the-art diffusion model, Diffusion Transformer XL, but by a decent bit, but it also reduces the image tokens by 64x, right? And so this model, they're saying, scales even better than the previous state-of-the-art, right? So you're able to take a model, and so if we go back to the theory here, the theory that they're proposing is that the adjacent tokens have like duplicated information. And so if you're removing the duplicates, this scales even better as the image you're trying to look at scales. Because now, instead of removing duplicate information, let's say information is duplicated from 1 pixel to, say, all the pixels neighboring, so 4 neighboring pixels. If you double the resolution, you also square the number of pixels. So you effectively, as the number of pixels goes by 4x, because you're not having any duplicates, you're storing like 4x less information, which is just natively much better, right? And so that's the theory that they're going for. And as they say, 410x faster generation process. Their best performing variant significantly surpasses the previous one while generating higher quality samples 74x faster, right? So they're basically saying we have a new idea on how to do any of this, right? And it scales much better than the previous things. Like they're able to beat the previous state of the art. And so we'll look at how they do that in the other sections. So now we can go back up to the image. And so the image, they're talking about TyTalk, which is theirs. They have VQGAN, which was previously the state of the art, and then you have the actual real image, 256 by 256. Right, and so as we can see, VQGAN is just 256 tokens, whereas TyTalk is 32 tokens, a lot smaller, right? You can feed this to a bunch of stuff. And so if you actually look at these images, you can see they're actually really good at like maintaining a lot of the information that's there, right? And so like it just keeps a bunch of the information, and it's a lot smaller, right? So you can also think of this sort of like an image compression paper, right? So you can store like images, you can compress them down, and there you go, right? Well, okay, cool. So now let's talk about the actual introduction. And so in recent years, image generation has experienced remarkable progress driven by advances in both transformers, and they link a bunch of transformer-based image generation models and diffusion models, and they linked a bunch there. And so basically, the image models, they're saying, is mirroring the trend in language models where they incorporate a standard image tokenizer and detokenizer, right? And so this kind of makes sense, right? So if you think about how a diffusion model works, a diffusion model takes an image and then also a prompt, right, a bunch of prompt tokens, and then it just kind of makes it slightly better to slightly more closely follow the prompt, right? And so to actually generate a full image via diffusion model, you'd run it through like 50 times, right? You take like a pure noise, and then you run it through, and you run it through like a few more times, right? And so where the diffusion models actually work is they first tokenize the image, and then they send it through an embedding model and go through diffusion, and then out it comes on the other side, right? And so so they basically just, and they basically the point of these tokenizers is to take the pixels from into like a latent space, and a latent space is basically just like the space of possibilities at the end of like a neural network layer, right? And so if we go back here, if we say go back here, right? So a latent space is in essence just the space in between the layers, right? And so the entire output of the neural network will just be a vector in whatever n-dimensional embedding space you're working with. right? And so the entire latent space is just this space that's of this n-dimensional vector. And so as the model improves, it will fine-tune the positioning of the stuff in the latent space. And so the point of these models is to just take images, which are like a pretty well-defined space, and turn it into this latent space, right? And so they tokenize it and put it into a pseudo-latent space, right? So you have to quantize it and whatnot. And so the latent space, which is 32 by 32, is significantly more compact than the original space, right? It is a compressed, like you're compressing the image effectively. It's a lossy compression, right? But you're compressing in such a way where it's easy for another model to take the output and run with it, right? And so the real big thing that this paper asks is, and let's finish off the introduction before we talk about the new stuff they've added. So image tokenizers have great success in image generation workflows. They have a fundamental limitation, right? They assume that the latent space should be 2D, right? So to maintain a direct mapping, right? And so it's a logical assumption for people to make, right? Like, hey, I'm trying to take this image that I have and try to make it into a format that's easier for a neural network to handle, right? And so logically you'd be like, oh, maybe I should retain the 2D aspect of the image because, you have a pixel, you have to make sure it's 2D. But what these people are saying is the 2D structure necessary for image tokenization, right? So they're asking, does the image actually have to be 2D, right? Can they encode images into a 1D sequence of a predetermined number of tokens, right? And so they're basically like saying, do we need to maintain a 2D structure, or can we get even better results if we remove the structure and let the neural net handle it itself, right? And so they're talking about other issues and whatnot. And so in this work, they introduce a transformer-based framework, right, like vision transformers, similar to last stream, right, designed to tokenize an image into a 1D discrete sequence, which can later be decoded back to the image space via a detokenizer, right? So if you guys remember if you guys know what a autoencoder is, right? So you take in essence, you take a space, right? So you take like an image, and then what you do is in essence, you compress it down into a much smaller space, and then you effectively are able to like turn this around and get the original thing back, or like something close to it. And so what the neural network here will learn is it'll basically learn how to compress the image to a smaller space and then be able to bring it back up to the full space, right? And so what a tokenizer is the tokenizer is doing something very similar, right? You take an input thing, you compress it down into a much smaller space, and you're able to bring it back up to the original. And so that's what these people are doing. That's what basically every image tokenizer is doing, right? So you take the original image, you gotta compress it, and the compression should be easy to use for neural networks, right? And so these people, they introduce TiTalk, which consists of a vision transformer encoder, a vision transformer decoder, and a vector quantizer following the tip. It's just a vector quantizer, right? It does quantization. So in the tokenizer, the image is split and flattened into a series of patches, right? Remember from the vision transformer paper that first you take the image, you do it in a bunch of patches. You have a bunch of patches, and so we're going to ignore the image patch embedding and just have the position embedding. And then you just apply attention and MLP across the entire image, right? So you take a bunch of patches, you take the image, you split up into a bunch of patches, and then you apply attention and MLP, and then you get another like thing, right? So they're basically explaining they do the encoding and they get latent tokens that build latent representation. Then they do quantization, and then the vision transformer is effectively used to reconstruct the input images from the masked token sequences, right? So you take the image, basically you compress the image, and then you basically pull it back up to its full resolution, right? And so they're basically building upon the research they just did here. They want to probe the dynamics and basically try to investigate it better. And so they're trying to do the interplay between latent space size, model size, because they're just trying to find out what happens if you scale it up, right? So here is the models they've made. Right, so GFID is a benchmark on tokenizers ish, and so they're basically just like, so on the right is better models, and up is just speed, so how fast can you do it. And so then what you have is, wow, look, TyTalk L, B, and S, they're just much faster for the same level of performance, right? This is a much more scalable architecture, right? It scales. And so the speed is measured on A100 GPU, which is kind of like a standard before the H100 happened. But yeah. And so in light of the findings, they introduce the thing. Now they're going to talk about related work, right? So they have quite possibly a ton of acronyms, right? You have a lot of acronyms here, right? So you have VQ, variational autoencoders, so vector quantized variational autoencoders. You have vector quantized GANs. You got vision transformers, vector quantized GANs. You just have a bunch of like other processors that all have their own acronyms and whatnot, right? So they're basically saying they're exploring 1D sequence length. Other people have also done the same thing. They're also saying, hey, we can use these tokens for image understanding, right? So you can feed this into multimodal LLMs, MLLMs, or VLMs, or whatnot. And so you can effectively feed this into a model and then get output out and whatnot. You can use this for image generation, right? It's just an image tokenizer. And then you have an illustration of what the model actually looks like, right? So as you can see, we get the same like autoencoder style structure, right? So you have the input, you try to encode it, you quantize it, and you just get a bunch of tokens, and you expand it out to reconstruct it, right? And so latent tokens, mask tokens, and basically that's the image generation, right? So similar, yeah, they just fill out the mask. And in the tokenization thing, again, image patches, latent tokens, you have the vision transformer, and then this is a bunch more latent tokens in latent space. Then you quantize it into just a list of numbers, and then with this list of numbers, you're able to decode the latent space, and then boom, you have your picture of a cat back, right? So you're compressing it, decompressing it, and then this is just, as you can see, lists of numbers. Very similar to a transformer model's list of numbers feeding in, right? So you just have these lists of numbers, and again, compression, decompression. And so this is like a preliminary background on vector quantization, variational autoencoders. So what happened previously is you have, so a typical vector quantization model, similar to what they're trying to do here, has three components: an encoder, a quantizer, and a decoder. So if we go back to here, right? So in essence, let's expand this a little bit more, right? So let's add one more step here. Let's add, and then I'll label the steps now as well, right? So you have the input image, and you have the input image again, hopefully, right? Like you're obviously always going to get some compression, going on here. You have the decoder. I should need to rotate the text. That's fine. You have the encoder, and you have the vector quantizer, right? And then you have, your tokens, right? I'm just gonna copy these down here. Let's put this on top. And then you have your tokens, right? So you have your input image, and you like quantize it down, and then you get your tokens, and you're able to decode it back out, right? So this is kind of what a variational autoencoder was, right? So you have your encoder, quantizer, and decoder. And these are all models you train. So, again, they go into a little bit more math, right? Like where you have the image, and then you put it into an encoding space with latent embeddings, then you downsample. You do a bunch of things. What these guys have done is, I should probably copy and paste this and basically be like old method, new method. I guess we have this here. Oh. Right, so old method is you'd have all of these, and they'd be in a 2D grid, right? So you'd have all of these in a 2D grid, and then you'd be able to decode it from there, right? So you're baking in the 2D-ness of your data. And then your vector quantizer and whatnot, basically what they're saying is they're basically just saying we're able to take this and effectively expand it, right? So it's like it's a 1D, but it's less data and a whole bunch of stuff. I just want to label these. EQ-VAE. Vector quantized variational auto coder. Right, so you have this, and then you also have Tightalk, which is transformer based 1D tokenizer. Right, I forget if that's the exact acronym, but it should be roughly around there. And so their main thing is, hey, we're just going to have this be a 1D model. And so they basically, yeah, so first you do an encoding model. So you take the image, right? And then you do a patch embedding layer. So if we go back here, they basically they include the patch embedding, and then they also have the positional embedding, and they just have the other latent tokens, right? So if you have another model feeding into this, right, like for example, you have like say the text of an image, like the captions under an image, and then you also want to feed that to the model, so it could be more accurate, right? And so then they basically just convert it to a list of patches, right? It's a 1D list of patches, similar to the vision transformer, just going like 0, 1, 2, 3, 4, 5, all the way up. They just have a list of patches, and then they just concatenate it together, similar to what happens normally. And so they do patch embeddings, they do latent embeddings, whatnot, and then they basically, in order to bring it out, they basically just quantize it, and then you can mask it if you want, and then you do a decoder, right? And so it's basically just saying, despite the simplicity, we emphasize the concept of compact 1D image tokenization remains unexplored, right? They're basically saying, we have this new thing. Everybody else, they're thinking 2D because that's just a natural thing to do. We're bringing in the 1D representation, right? So that's what these people are saying. And we can scroll down and we can see their results, whether or not they're good or bad or whatnot. So they're talking about the training strategy, existing training strategies. Well, they're basically saying they have two-stage training, right? So what you normally have for, let's say, a regular model is you just have a one-stage training, right? So you have training data and you just train it and then you have your model. For larger LLMs, right? For example, like GPT-4, first you had the pre-training step where you train on as much data as you can. Then you have the instruct fine-tune, so now the model knows how to chat specifically in the format you've given it and whatnot. And then you do RLHF to make sure the model is not like racist or whatnot, right? These people, they're saying they have a two-stage training, right? So first you have a warm-up and a decoder fine-tuning stages. So basically in the warm-up, they basically, instead of just going directly on RGB, they just train it with discrete codes from an off-the-shelf model. So they basically just have two steps here. The first step is they train the model on effectively just the outputs of a previous state-of-the-art model. So they're able to take that, bring that in here. And after that, they're able to do more regular training. So they're basically just saying, hey, this doesn't actually harm the functionality. It just makes it closer to the regular one, right? So basically, they're able to train these separately with the expectations of a previous model. And so then they have the experimental results. So first, they have a few different models, right, of three sizes, 22M, 86M, and 307M for the encoder and decoder respectively. And so small, base, and large. And then they also impact the varying number of latent tokens from 16 to 256. So they have like two different test dimensions, right? One, which is the size of the model, and the other is in essence, the number of tokens they're actually compressing it down to, right? And so then they have an evaluation protocol, and then here is the graph for how good their model is, right? So small and mediums, or base as they're calling it, is these, and then this is their large model. So as we can see, RFID, lower is better here. So as you can see, the bigger model performs better than the smaller models, and as you scale up the number of tokens, you basically optimize like how good it is, right? And so as we can see, you kind of get a lot of diminishing returns past like 64 tokens, but it has a nice scaling law. So if you need better results, you can always just scale up bigger and bigger. And they also have masked the GITV GAN, which is one of the previous state of the art, and they basically say at 256 tokens, which is what this one goes to, they've effectively matched it with their large model. And the taming VQ GAN, which is another one of the state of the arts, they're basically saying they're doing a lot better than, right? Even with the small model. So the number of latent tokens in a 1K probe. So this is basically, oh, this is the accuracy. So this is the accuracy at tasks, as you can see. Wait, what? Linear probe accuracy. What's B? Okay, I don't actually understand what B is saying. I'm going to be real. I don't actually understand what B is saying. This is more research for later. Generation FID. Again, lower is better. This is just another benchmark. So, as you can see, this one just drops like a cliff, right? Like at 64 tokens, we're already doing better than mass GITV QGAN at 256 tokens and whatnot, right? Like, and then again, you have speed, right? So, as you have more of these, as you're generating more tokens and you're trying to constrain the model less, you're able to, it goes slower basically because you effectively have a bigger model. So they're basically just saying, if you're compressing it more, you have a much faster model. And so, yeah, and so scaling up enables a more compact latent size. And so I believe they showed us later in the paper where they don't get to it yet. Okay, basically, if you're able to make the model bigger, you're able to use a smaller size. So if we go back here, right, you can see that if you want roughly around like a 7-ish on RFID, it's 32 tokens with the largest model, 64 with the medium model, and 96 with the smallest model, right? So in essence, the bigger you make these models, the better they scale effectively. Well, not better they scale. The better they do, right? So you're able to compress it more the bigger you make the models. But that also comes at the cost of performance, obviously. So the semantics emerge with a compact latent space. It's compact, and it improves generative training. So they did some tests on whether or not it was good at downstream tasks, and so they combined it with a bunch of stuff, and their stuff ends up being the best, right? It's best at downstream tasks. And so they have a few sizes, and I think the best results, clearly, right? So they're basically saying they're basically smaller than everybody else. And so the best results is probably from the pictures they have, right? So they have, a bunch of references. And so here is effectively how well the models do at different scales. So the large model, they're doing at 32, the base at 64, and the small at 128, right? And so as you can see, these perform very similarly, right? So you're able to, as they're shown here, you're able to compress it to, so the 32 tokens they got in the title comes from the actual largest model they trained, right? And so here we can see the effect that having more tokens or increasing model size actually has, right? So as they're saying, right? So this, effectively, this is as close to the original image as you get. It's a pretty good picture of a blue jay, right? So 256 tokens, largest model, it's going to be the best you have, right? But as we can see, this blue jay has, it's lost the blue. There's no more blue in this blue jay, right? This blue jay doesn't actually have a lot of the more fine details. It doesn't have, for example, the beak's not the right color, right? But we also see similar effects with this. So the smallest model requires twice as much tokens to get the information across as the medium model. Whereas the largest model, you can actually do better, right? And so you're effectively, as you can see here, you're effectively able to do better with the larger model, which is that's more computationally expensive, right? It's more expensive to do those types of stuff. And so there's a license and whatnot. And so, again, if we go back to here, they're basically, this group, their main new bit of research is, hey, if we have all the tokens that this transformer model outputs, right? So this encoder is a vision transformer, right? If you have all the tokens that this outputs, that's just going to be in the same format. That's not the same format. But like if we change the format, that's going to be much better in terms of compression and like accuracy and whatnot, right? So you're able to make a much better tokenizer if you remove the thing forcing you to maintain it as a 2D tokenizer. And that's the main thing that this paper adds. Now next stream we're going to go and we're going to talk about the chameleon model, right? So this builds on basically all the stuff from previous streams. Right? You're going to talk about vision transformers, you're going to talk about image tokenizers, basically all that type of stuff. And this is actually bringing it in to an LLM, right? So you're able to make a multimodal LLM out of this type of stuff. And I think I'm going to leave this stream for that. I think after the stream, when this becomes a YouTube video, I am going to actually paste the link to the draw.io in the description. I should also probably put that in the description of this stream. That's for next stream. And next stream we'll talk about the chameleon model. And hopefully that's probably on Friday, maybe on Saturday. And that's basically it. I will be seeing you guys all next stream.